Welcome. We are looking at the applications and we are looking at how to use phase field model to model some of the microstructural features that one typically sees. We have looked at spinodal, we have looked at ordered domain growth, we have looked at grain growth and so on. So, the problem that we want to discuss today is what is known as grain boundary grooving. Now, what is the grain boundary grooving? Let us assume that I have a grain structure, which means there are two grains, and let us also suppose that this grain boundary separating these two phases is cutting the surface in a perpendicular manner. So, it is like this. So, I have a surface and I have a grain boundary. So, this is grain 1 and this is grain 2, and let us say that this is vapor. Okay. So, there is no grain. So, we have a surface and that surface consists of two grains. So, this is a grain boundary and obviously, this surface has an interfacial energy, let me call that as gamma surface vapor, and similarly this has a gamma surface vapor and this has gamma grain boundary. Now, as one can see at this point there is an imbalance of forces, because this gamma SV and this gamma SV can cancel out each other, but this gamma grain boundary is unbalanced, right. So, these interfacial energies can be thought of like surface tensions. Let us assume that they are all isotropic and no dependence on different grain boundaries, for example, the surface vapor energy, and this grain boundary energy is also like some surface tension, let us assume. If you assume that, then these forces need to balance. So, to balance the forces, the system is going to produce what is known as a grain boundary groove. So, this is the perpendicular. So, the grain boundary near this point is going to take a shape, let us say that this angle is theta. Now, this gamma SV will get split into two parts. So, it will be gamma SV cos theta and there will be a gamma SV sin theta component, and so there will be another gamma SV. Suppose let us assume that this is a symmetric groove, then you will have two gamma SV cos theta in the perpendicular direction and this is gamma SV sin theta. Now, this 2 gamma SV cos theta can actually balance gamma GB. Okay. So, gamma GB is 2 gamma SV cos theta. So, the groove angle theta is going to be gamma GB by 2 gamma SV cos inverse. So, it is going to go towards this structure and such a groove is known as a grain boundary groove. Now, there are many different physical scenarios and many different reasons for grain boundary grooving. For example, if the other phase is not vapor, but it is a liquid, what happens to the boundary groove? So, there also there will be grooving, except that the energy that it will balance will be the liquid melt and the solid surface energy. So, gamma SL. So, 2 gamma SL will what be balanced by the gamma GB. So, there will be a groove angle, and grain boundaries also happen to be regions of fast diffusion. So, sometimes if there are liquids can go through the grain boundary and lead to other interesting effects. Sometimes grain boundary grooving is also useful. For example, if you put a sample which has a flat surface in the furnace for a while, then all the grain boundary regions get grooved, then it is easier to look at the grain structure and where the grain boundaries are, because there are grooves where the grain boundary is. So, you can take it to a microscope and easily look at the microstructure using grain boundary grooves. So, typically you have to take a sample and you have to polish it. After polishing, you have to etch it, so that the grain boundary regions are preferentially removed. So, you can see under a microscope easily the grain structure. So, some samples, typically some ceramics samples where it is very difficult to polish and things like that. So, grain boundary grooving could be a mechanism which is like equivalent of etching for metals and alloys to look at the grain boundary structure. Now, this is the system that we want to model, a grain structure. So, you have two grains meeting at a flat surface with vapor. At that point they are going to groove. So, this is the structure that we want to model. So, obviously for the phase field model, first we need to decide on how to describe this microstructure, and we want to use a Fourier transform technique to solve this problem. So, we are going to use the periodic boundary condition. So, we need to come up with an initial profile which is periodic, and then we are going to write the free energy. From there we are going to derive the evolution equations, and then we are going to solve the problem. So, that is what we want to do in this lecture. So, now that this is the given geometry, so let us find out how to model this using the phase field model. So, for doing the phase field modeling, I am going to assume that the microstructure that I am going to look at is looking like this. Remember that I need periodic boundary condition. So, I am going to assume that this is solid and this is vapor and this is solid. So, I have solid here, I have solid here, by periodic boundary condition that is satisfied. Okay. Now, I am going to put a perpendicular boundary. I am going to put a perpendicular boundary. Now, typically one might tend to think that there is only one grain boundary, right. So, I have grain 1 here, I have grain 1 here and grain 2 here. So, the periodic boundary condition here also is satisfied, grain 2 continues to grain 2, grain 1 continues to grain 1. So, there is a grain boundary between them, but this is not the only grain boundary because of periodic boundary condition, because this is going to repeat here. So, there is a grain boundary here, because by periodic boundary condition grain 1 is sitting here. So, grain 1 and grain 2 say there is a boundary here, there is another grain boundary here. Okay. So, there are in all 3 grain boundaries. Okay. This is the case for which we are going to write the code and solve the problem. Of course, as a tutorial, for example, you can take the other geometry and try to solve the problem. So, in terms of solid, vapor, solid, it has the same structure, and then we say that this is grain 1 and then this is grain 2 and this is grain 1 again. In this case, you can manage with only 2 grain boundaries instead of 3 grain boundaries like we have here, but effectively this is also only 2 grain boundaries, because this and this is the same boundary by periodic boundary condition. So, we are dealing with 2 grain boundary case, except that one of the boundary is split apart because of our periodic boundary condition. Now, if this is the structure, the initial structure that we are going to take. Now, how do we describe this microstructure? Of course, to describe this microstructure, we need at least 3 order parameters. So, what are they? I need order parameter which is conserved order parameter, which is like C, normalized in such a way that vapor will have very little of this material. So, C equal to 1 in solid and C equal to 0 in vapor. This is the first order parameter. The second and third order parameter, of course, are the ones which represent the grain structure. So, that means they will be phi 1 and phi 2. Now, wherever phi 1 and phi 2 are there, because they represent grain structures, the minima should be such that phi 1 phi 2 C equal to 1. Okay. So, that is either phi 1 equal to 1 or phi 2 equal to 1, means C equal to 1. Only when phi 1 equal to 0 equal to phi 2, then C equal to 0. That is, in vapor there is no grain orientation 1, there is no grain orientation 2, there is no composition, right. So, let me assume that this is like pure copper, for example, there is very little of copper. So, I can say that 0 copper and no orientation 1, no orientation 2, that will be vapor, and in grain 1 phi 1 will be 1, and because it is a solid, C will be 1, but grain phi 2 will be 0. In grain 2, on the other hand, phi 1 will be 0, phi 2 will be 1, C will be 1. So, this is the order parameter that describes the microstructure. So, if we say that this is the description, then the job is to write a free energy functional which will have all these properties. This has been done, in the group where I was doing my PhD more than once. In fact, the first thesis, a master's thesis on this on phase field modeling in this country was written by one Professor Subhradeep Chatterjee. He wrote it for the grain growth, grain boundary grooving problem, and later Professor Rajdeep has solved this problem. So, we are going to use the free energy functional that is given by Rajdeep in his PhD thesis. They have taken into account all these minima and how the free energy should behave, everything. So, our job becomes easier. So, what is the free energy functional that was used in terms of the free energy structure? What Subhradeep used and what Rajdeep used, they are not very different, but we will go with what Rajdeep used. So, the free energy now is a function of C, phi 1 and phi 2. So, this is the bulk free energy density, right. So, we have this part which is the bulk free energy density, and we need to give this F in such a way that it will obey all these conditions, and the total free energy will be actually an integral over volume of F of C comma phi 1 comma phi 2 plus K C del C squared plus K phi 1 del phi 1 squared plus K phi 2 del phi 2 squared, right. So, this is the total free energy for which we are going to write the Euler-Lagrange equation. Now, what is the form of this F of C phi 1 phi 2? So, that is what I want to describe now. Has this structure A C squared into 1 minus C whole squared. So, this is going to make sure that there is a minima for C equal to 0 and there is a minima for C equal to 1. This we have been using for quite some time now. Now, to couple, to make sure that when C equal to 0, the minima also has phi 1 and phi 2 to be equal to 0, we are going to write the next part, that is B C squared and some function xi of phi 1 and phi 2. Okay, I will write down what this function xi is, plus some z times 1 minus C whole squared. So, when C equal to 1, we want both phi 1 and phi 2 to have their value as 1, either phi 1 or phi 2 to have their value as 1. So, that solid C equal to 1 will correspond to some orientation. So, that coupling is taken care of by this phi 1 squared plus phi 2 squared. Okay. So, now the only thing we need to describe is this function of phi 1 comma phi 2. Of course, this will have the required double well potential in terms of phi 1 and phi 2. So, it is phi 1 power 4 by 4 minus phi 1 squared by 2 plus phi 2 power 4 by 4 minus phi 2 squared by 2 plus 2 phi 1 squared phi 2 squared plus 0.25. Okay. And so, now why is this the free energy that has all the required properties? Of course, you can do the plotting of this free energy under different cases, and you can look at what happens to this free energy. So, that also we will do as a tutorial, but for now we now have a free energy functional. So, once we have the free energy functional, it is possible to develop the evolution equation. So, to do that, so let me write down the free energy expression in complete. So, now I have F by NV as nothing but F plus kappa C del C squared plus kappa phi 1 del phi 1 squared plus kappa phi 2 del phi 2 whole square dV, and this F is nothing but A C squared 1 minus C whole squared plus B C squared some function of phi 1 phi 2 plus Z 1 minus C whole squared phi 1 squared plus phi 2 squared, where this function is has this phi 1 power 4 by 4 minus phi 1 squared by 2 plus phi 2 power 4 by 4 minus phi 2 squared by 2 plus 2 phi 1 squared phi 2 squared plus 0.25. Now, we need to know all these A, B, Z, kappa C, kappa phi 1, kappa phi 2, etc., and again they have been chosen appropriately. We are going to, and they are non dimensionalized. So, A, B, Z all are taken to be equal to 1, and kappa C is taken to be equal to 1, and kappa phi 1 equal to kappa phi 2 equal to 1/3. So, this is the values that we are assuming. Now, we need to look at the evolution equation. Of course, because there is one conserved order parameter, you have to write the Cahn-Hilliard equation for that. So, dou C by dou T, we would assume that the mobility is constant and it is unity. So, m del squared acting on mu C, where mu C is nothing but del by del C. And as you can see, this variational derivative is going to give me K C del squared C with a negative sign, of course, and this is going to give me dou F 0 by dou C, right. So, that dou F 0 by dou C then is has to be differentiated. So, this will give 2 A C 1 minus C 1 minus 2 C. When you differentiate, this will give me 2 B C, this will give me minus 2 Z times 1 minus C multiplied by this corresponding quantity. Similarly, for dou phi I by dou T, we are going to use minus L I mu phi I. What is the mu phi I? That is nothing but delta of F by N V del phi I. Okay. So, I is equal to 1 and 2. So, there are going to be 2 equations. So, totally there are 3 equations, one Cahn-Hilliard and the other 2 are Allen-Cahn equations, and of course, we know how to deal with these equations in the Fourier space. So, all that is key to this model is this free energy functional. If you choose the free energy functional correct, and if you use the correct parameter values that the minima has the required property, namely when C equal to 0, both phi 1 phi 2 will be equal to 0, that is the minima. When C equal to 1, either phi 1 or phi 2 has to be 1, the other one has to be 0. So, that is the minima, in which case you will have 3 minima corresponding to the vapor phase, grain 1 and grain 2. and we know what is the initial structure that is consistent with periodic boundary condition. So, now knowing the evolution equation, knowing the parameters that go into the evolution equation, we can then implement it in Octave and look at whether the grain boundary starts grooving if we start with a flat solid vapor surface which has a grain boundary cutting to it in a perpendicular fashion. Okay. So, that is what we will do. So, we will try to model this problem in Octave and see what happens to the evolution of the microstructure. Thank you.